At the bottom of the ocean, time behaves differently. There are no sunrises, no seasons, no familiar rhythms to anchor expectation. Just pressure, darkness, and an acoustic world where sound travels farther than light ever could. So when a signal began appearing, quietly, persistently, every 27 minutes it did not arrive as a shock. It arrived as a problem. Not because it was loud, not because it was dramatic, but because it was regular. In science, repetition is supposed to be comforting. It suggests order, predictability, understanding. But this signal offered none of those things. It repeated without identifying itself. It continued without escalating. And most unsettling of all, it did not behave like a one-time event. It behaved like a process. In the early 2000s, global ocean monitoring entered a new phase. Advances in hydroacoustic sensors, originally developed for submarine detection and seismic monitoring, were being repurposed for civilian science. These instruments were extraordinarily sensitive. They could detect distant earthquakes, iceberg calving, underwater landslides, even the low-frequency calls of whales traveling across entire ocean basins. Arrays were deployed quietly, permanently, listening not for any single sound, but for patterns over time. That is how the signal was first noticed. Not during a crisis, not during an expedition, but during routine data review. A low-frequency pulse, faint, repeating, roughly every 27 minutes. At first, it was cataloged without comment. Ambient noise is full of quirks. Oceanographers expect irregularity, storms, shipping traffic, biological activity, thermal layers. Anomalies are common. Patterns are not. But as weeks turned into months, the signal did not disappear. It kept time. Technicians ran the usual checks. They ruled out mechanical interference. The timing did not match any onboard systems. Maintenance logs showed no cyclical activity that aligned with the interval. Seismic explanations were tested next. Micro-earthquakes can repeat, especially in tectonically active zones. But seismic events do not behave this way. They cluster, they decay, they vary. This signal did none of that. Its interval drifted slightly over long periods, but not randomly. The variation suggested adjustment, not noise. The amplitude remained within a narrow range, and critically it appeared across multiple sensors, separated by thousands of kilometers. That eliminated local error. What remained was uncomfortable. A repeating deep-sea signal that did not fit into any established category. To understand why that mattered, it helps to understand how ocean acoustics are classified. Most sounds fall into known families. Seismic, earthquakes, volcanic activity, tectonic stress. Mechanical, ships, drilling, infrastructure. Biological, whales, fish choruses, crustaceans. Environmental, storms, ice movement, wave action. Each has characteristic signatures, frequencies, durations, patterns of variation. This signal sat between categories. It was too regular for geology, too slow for machinery, too consistent for biology, and it lacked one defining feature scientists rely on: a known cause. So officially, it was logged as something deliberately vague. Unclassified ambient noise. A placeholder, not a conclusion. As more data accumulated, a small group of researchers began tracking the signal's movement. Not in space, but in time. They overlaid years of recordings. The signal was always there. Sometimes stronger, sometimes weaker, but never absent. And it did something else that defied expectation. It propagated. Not outward like an explosion, not inward like a collapse, but across sensor networks in a way that suggested continuity, as if the source was stable, but the medium through which it traveled was changing. This made attribution harder. If it had been a one-off event, it could be dismissed. If it had grown louder, it would have triggered alarms. If it had stopped, it would have faded into background noise. Instead, it persisted. Quietly, reliably. And that reliability made people uneasy. At conferences, the signal was mentioned, briefly, always with disclaimers. No clear origin. Likely environmental. Under further review. But noticeably, no one named it. Naming implies ownership, definition, responsibility, and assigning a name to a phenomenon suggests confidence that it belongs somewhere in our understanding of the world. Here, confidence was absent. Emails from the period, later referenced in secondary analyses, show researchers urging caution, not because the signal was dangerous, but because interpretation risked speculation. One phrase appears repeatedly in internal discussions. Let's not get ahead of the data. That sounds reasonable, but it also marked a shift. The signal was no longer being chased, it was being contained. Scientific investigation depends on incentives. Funding follows clarity. Outcomes, relevance. This signal offered none of those. It didn't threaten infrastructure. It didn't correlate with seismic risk. It didn't align with known marine species. And most critically, it did not demand action. So priorities shifted. Sensors were retasked. Analysis time was allocated elsewhere. New projects promised clearer results. The signal was still recorded, but it was no longer pursued. That distinction matters. Because what science chooses not to investigate often tells us as much as what it does. By the mid-2000s, the deep-sea signal had become something strange. Not a mystery being solved, not an anomaly being disproven, but a known unknown, acknowledged, archived, and quietly avoided. It continued every 27 minutes. Through changing technologies, through shifting research agendas, through decades of listening, which raises the question that will define the rest of this story. If the signal was meaningless, why did researchers stop trying to name it? And if it wasn't meaningless, what made giving it a name feel so risky? In the next part, we'll follow how the signal was tracked across oceans, and why the moment scientists realized it behaved like a process, not an event, everything changed. By the time researchers accepted that the signal was not a local anomaly, it had already rewritten the rules of how they were allowed to think about it. Because events can be explained. Processes demand context. And this signal behaved like something that continued, not something that happened. Once that distinction became unavoidable, the investigation quietly crossed a line. To track a sound across the ocean is not as simple as following a trail. Sound underwater bends. It refracts through layers of temperature and salinity. It accelerates in cold, dense water and curves away from warm currents. What appears to be a single source can fragment into ghost echoes, or converge from multiple origins into one illusion. Which is why, when researchers began comparing data from distant hydrophone arrays, they expected confusion. Instead, they found coherence. The 27-minute signal appeared in datasets separated by thousands of kilometers. Not simultaneously, but sequentially, in ways consistent with long-range acoustic propagation. The timing shifts matched known ocean sound channels. The amplitude decayed predictably with distance. This was not random noise repeating coincidentally. It was one signal, traveling. That realization forced a recalibration of scale. Whatever was producing the sound was not local. It was not confined to a single seafloor feature. And it was not short-lived. It occupied the ocean as a system. Once scale enters the picture, explanations narrow. Localized geological activity could no longer account for it. The ocean floor does not host synchronized processes that pulse globally every 27 minutes without variation. Mechanical sources were reconsidered. Could it be shipping? Submarines? Industrial infrastructure? The problem wasn't just the frequency, it was the regularity. Human systems are noisy. Maintenance cycles drift. Schedules change. Mechanical systems fail or get replaced. This signal did not. It repeated through holidays, geopolitical shifts, economic downturns, and technological upgrades. Its persistence outlived the very instruments used to first detect it. Biological explanations were revisited next. Certain whale species produce low-frequency calls that travel enormous distances. But biological rhythms are adaptive. They change with season, migration, breeding cycles. This signal did not follow seasons. It followed time, and that distinction unsettled people. At this point, the signal acquired an unofficial label among researchers. Not a name, more like a shorthand. The 27-minute pulse. That phrasing was intentional, neutral, descriptive, non-interpretive. Still, even that was used sparingly, because once something is discussed consistently, it begins to accumulate meaning. And meaning invites questions that science is not always prepared to answer. One oceanographer later described the atmosphere this way. We weren't afraid of what it was. We were afraid of being wrong about what it wasn't. That fear shaped everything that followed. As tracking improved, a more troubling feature emerged. The timing wasn't perfectly fixed. Over long timescales, years, not days, the interval drifted by small but measurable amounts. Sometimes the pulse arrived a few seconds early, sometimes a few seconds late. Not randomly. The drift showed pattern. When ocean conditions changed significantly, large-scale temperature anomalies, major current shifts, the timing adjusted subtly. Not enough to suggest response, but enough to suggest coupling. This was no longer just a repeating signal. It was interacting with its environment. And interaction implies mechanism. This is where researchers slowed down. Not because the data became weaker, but because it became harder to talk about without crossing into speculation. If the signal adjusted to environmental conditions, then it wasn't a passive artifact. But calling it responsive raised questions no one wanted to frame publicly. Intent was never proposed, but even implying adaptation was considered risky, so papers softened their language. Correlation, possible coupling. Further study required, and further study never quite arrived. Footage from oceanographic conferences during this period is revealing. Not for what is said, but for what isn't. Presentations on ambient noise would occasionally show plots where the 27-minute pattern was visible. No one highlighted it. No one asked about it. The slides moved on. In hallway conversations, it came up, briefly. Always with a shrug. Always followed by a redirect. Probably nothing. Hard to pin down. Not our focus right now. This is how scientific attention narrows. Not through censorship, but through consensus about what is worth discussing. The signal wasn't denied, it was deprioritized. At some point, someone suggested giving the signal a formal designation. Not a dramatic name, just a catalog identifier. Something to anchor a future discussion. The proposal stalled. Because names imply legitimacy. Once something has a name, it can be searched, tracked, referenced. It becomes harder to quietly ignore. And ignoring the signal had become convenient. It didn't fit funding categories. It didn't align with research mandates. It didn't promise solutions. It only raised questions. By the late 2000s, deep-sea monitoring priorities shifted. Climate-related acoustics took center stage. Ice dynamics, storm modeling, anthropogenic noise impacts. Sensor bandwidth was finite, analysis time limited. So the signal remained in the background, still recorded, still present, still repeating, but no longer interrogated. This is where the story changes character, because the mystery is no longer about what the signal is. It's about what happens when science encounters something persistent, coherent, and unexplained, and decides that naming it would create more problems than it solves. By this point, the deep-sea signal had done something subtle but profound. It had revealed a boundary, not in the ocean, but in the scientific process itself. A boundary between observation and interpretation, between detection and acknowledgement. And that boundary was about to be tested, because in the next phase of this story, the signal would be encountered by systems that do not share human discomfort with ambiguity. Systems that detect patterns without caring whether they are convenient, fundable, or nameable. In the next part, we'll examine how automated analysis and long-term data synthesis brought the signal back into focus, and why, once machines began flagging it independently, avoidance became much harder to justify. The signal never asked to be understood. It didn't change volume to demand attention. It didn't accelerate to trigger alarms. It didn't vanish to invite relief. It simply continued. And when automated systems began noticing it, independently, repeatedly, without instruction, the silence around it became harder to defend. Because machines do not defer to tradition. They do not worry about interpretation. They do not avoid inconvenient patterns. They register what persists. By the late 2000s and early 2010s, ocean science entered a new phase, one defined less by expeditions and more by synthesis. Decades of hydrophone recordings were being pooled into centralized databases. Advances in computing made it possible to analyze long time series data at scales no human team could manage. What once required months of manual review could now be processed in hours. The goal was straightforward. Identify trends, climate variability, anthropogenic noise, baseline shifts in the ocean's acoustic environment. The algorithms were not designed to hunt anomalies. They were designed to compress complexity, find repeating features, reduce noise, flag deviations from expected distributions, which is exactly why the 27-minute signal reappeared, not as a mystery, as a statistical outlier that refused to smooth away. During early runs, engineers noticed something odd. When models were trained to characterize normal, deep-sea ambient noise, performance improved when a certain low-frequency component was left intact, even though it didn't match known categories. When that component was filtered out, prediction accuracy dipped slightly but consistently. That shouldn't have happened. Removing irrelevant noise is supposed to help models, not hurt them. So, engineers did what they always do. They inspected the features. And there it was. A repeating pattern, low frequency, narrow band, temporally structured, appearing across training datasets from different oceans, different years, different instruments. The same interval, every 27 minutes. The algorithms weren't told to look for it. They found it anyway. This raised an uncomfortable question. If the signal was meaningless, why did models rely on it? Machine learning systems don't invent structure. They exploit it. They gravitate toward features that improve internal consistency, even if those features don't align with human intuition. In other words, the signal was useful, not because it represented danger or intent, but because it helped describe the ocean more accurately than models that ignored it. That usefulness forced a reassessment, not of the signal itself, but of how it had been treated. For years, researchers had avoided naming it because it didn't fit existing frameworks. Now, those frameworks were being quietly bypassed. The next step was interpretability. In applied science, accuracy is not enough, especially in fields tied to policy, safety, and public trust. If a model relies on a feature, researchers are expected to explain why. And that's where things stalled. When engineers attempted to isolate the contribution of the 27-minute signal, they encountered a problem. The models didn't use it in isolation. They treated it as part of the background fabric, something stable enough to anchor other inferences. Remove it, and the statistical ground shifted. This made explanation difficult. What do you call a feature that improves understanding without representing a cause? What do you do with a pattern that matters mathematically but not conceptually? Faced with that dilemma, most teams chose the conservative option. They filtered the signal out. Not because it was wrong, but because it was unexplained. This decision wasn't framed as suppression. It was framed as risk management. Black box dependencies are dangerous. If a model can't justify its reasoning, it can't be trusted in high-stakes environments. So the signal was removed from pipelines. Performance dropped slightly, but predictably. Transparency was preserved, and the anomaly was once again pushed out of sight. This marked a turning point. For the first time, the signal was being actively excluded, not by human judgment, but by algorithmic design choices shaped by human discomfort. Even filtered, the signal left traces. Residual correlations, minor timing dependencies, subtle shifts in baseline noise profiles. Enough to suggest that the ocean's acoustic environment was being shaped by something persistent, something not accounted for in prevailing models. Some researchers began to ask a quieter question. What if the problem wasn't the signal? What if the problem was that our categories were incomplete? This was not a question funding agencies wanted answered, because answering it would require acknowledging that decades of ocean acoustics had overlooked, or deliberately sidelined, a stable feature of the system. Not dangerous, not catastrophic, just unexplained. Once machines began flagging the signal independently, the idea of formally naming it resurfaced. Again, the proposal was modest. No claims about origin, no speculation about intent, just documentation. But naming changes incentives. A named phenomenon attracts attention. Attention invites interpretation. Interpretation invites distortion. Administrators worried about headlines, about mischaracterization, about narratives escaping academic control. The signal, as long as it remained unnamed, remained manageable. Once named, it could not be quietly deprioritized. So, again, the proposal stalled. By now, a pattern had emerged. When humans detected the signal, they hesitated to interpret it. When machines detected it, humans removed it from consideration. When both converged, institutions chose silence, not denial. Silence. This wasn't conspiracy. It was convergence of incentives, norms, and risk aversion, and it worked. The signal continued. The research moved on. The anomaly remained unclassified, but something had changed. The signal was no longer just an acoustic curiosity. It had become a mirror, reflecting how science handles phenomena that persist without explanation. Because the deeper question was no longer about the ocean. It was about knowledge. What happens when a pattern is real, measurable, persistent, and yet incompatible with how we organize understanding? In the next part, we'll confront the most uncomfortable aspect of this story. Why giving the signal a name might force science to confront limits it would rather leave undefined. Because sometimes the most dangerous step isn't discovery, it's definition. At some point, every unresolved pattern stops being a curiosity and becomes a liability. Not because it threatens safety, not because it demands action, but because it quietly exposes the limits of the system meant to explain it. By the time the 27-minute signal reached this stage, the ocean was no longer the central problem. The problem was definition. Science depends on names more than it likes to admit. A name allows comparison. A name allows citation. A name allows something to be taught, funded, debated, and eventually resolved. Without a name, a phenomenon exists in a kind of intellectual limbo. It can be observed endlessly, logged indefinitely, and yet never fully acknowledged. The deep-sea signal had remained in that state for nearly a decade. Everyone working with long-term hydroacoustic data knew about it. No one officially recognized it. That ambiguity began to strain the system. Not because of external pressure, but because internal consistency was breaking down. You can only pretend something is irrelevant for so long before the pretense becomes visible. By the mid-2010s, younger researchers entering the field encountered the signal without the historical context that had shaped earlier caution. They didn't know it was sensitive. They didn't know it was better left alone. They saw it as what it was, a persistent feature of the data, and they asked the obvious question: why doesn't this have a name? That question landed awkwardly. Senior researchers answered carefully, vaguely, often indirectly. It's complicated. There's no agreed interpretation. It hasn't been formally classified. All true, none fully satisfying, because the absence of a name had started to look less like prudence and more like avoidance. At this stage, a few interdisciplinary teams attempted a compromise. They proposed documenting the signal without explaining it. No origin hypothesis, no functional claims, no speculation about intent or mechanism, just a formal description: frequency range, temporal regularity, geographic persistence. In other words, a catalog entry. This is a common scientific move when understanding lags behind observation. But here, even that step triggered resistance. Naming the signal would do something subtle but irreversible. It would turn an ambient irregularity into a recognized phenomenon. Once named, it could be referenced across papers. Once referenced, it could be aggregated across datasets. Once aggregated, it would demand explanation, and explanation was precisely what no one had. The concern was not that the signal implied anything extraordinary. The concern was that it implied nothing useful. No hazard, no application, no predictive power tied to known processes. Just persistence. Science is not built to accommodate that easily. Internal discussions, later recalled in interviews and conference panels, reveal a recurring anxiety. If the signal were named, what would stop others from projecting meaning onto it? Media misinterpretation, speculative narratives, public fascination detached from evidence. Once a phenomenon escapes its technical framing, nuance rarely survives. Administrators worried that even a neutral label could be misused, framed as evidence of hidden activity, intelligence, or unknown forces. Not because those claims were supported, but because the absence of explanation creates a vacuum, and vacuums attract stories. So the decision logic became circular but effective. The signal wasn't named because it wasn't understood. It wasn't understood because it wasn't studied in depth. It wasn't studied because it wasn't named. Each step reinforced the next. And importantly, no single person made that decision. It emerged naturally from incentives. Funding bodies preferred projects with outcomes. Journals preferred interpretations. Institutions preferred stability. Researchers preferred careers without controversy. The signal fit none of those priorities, so it remained where it had always been: present, persistent, and officially undefined. Avoidance has consequences, even when it feels harmless. Because over time, the unnamed signal continued to shape analyses indirectly. Baseline noise models incorporated it unknowingly. Comparative studies adjusted around it. Machine learning systems compensated for it statistically. In effect, ocean science adapted to the signal without acknowledging it. That adaptation masked its strangeness. The more normalized it became, the less urgent it felt to explain. This is how unresolved phenomena fade, not by disappearing, but by blending into assumed reality. Yet cracks were forming. As analytical methods improved, discrepancies emerged between models trained with different pre-processing assumptions. Teams filtering out low-frequency periodic components reported slightly less stable long-term predictions. Teams leaving them in couldn't explain why performance improved. The difference was small, but persistent. And persistence, as this story has shown, matters. It suggested that the signal wasn't just noise being tolerated, it was structure being ignored. Which brings us to the narrowing point of this story. The deep-sea signal had survived decades of observation. It had resisted categorization. It had influenced models without being named. And now, it had exposed a deeper issue. Not in the ocean, but in how science decides what deserves explanation. In the final part, we'll confront what the signal most likely represents, not by speculation, but by elimination. And more importantly, we'll examine why acknowledging that conclusion would force science to admit something it rarely does openly, that some patterns are real, persistent, and measurable, and still sit outside the boundaries of what our systems are prepared to explain. Every investigation eventually reaches a point where the question changes. Not what is happening, not how long it has been happening, but why we have tolerated not knowing. For the deep-sea signal repeating every 27 minutes, that point was never reached in the data. It was reached in the culture around the data. Let's establish what the signal is not, based strictly on decades of elimination. It is not seismic. Its timing does not match tectonic cycles, fault resonance, or earthquake aftershocks. It is not mechanical. No known industrial system, submarine cables, drilling platforms, naval operations, operates with this level of global regularity for decades without interruption. It is not biological in any known sense. Marine life produces sound, sometimes rhythmically, but not with this level of temporal precision, geographic persistence, and frequency stability. It is not an isolated artifact. The signal has been detected across independent sensor networks, operated by different nations using different technologies years apart. Each of these explanations failed quietly, not spectacularly. And when multiple explanations fail independently, what remains is not mystery. It is constraint. The most conservative conclusion scientists could draw was also the most uncomfortable. The signal behaves like a process, not an event. Processes have continuity. They have internal timing. They persist unless disrupted. That realization alone was enough to change how some researchers privately spoke about it. Not publicly, not in papers, but in hallways, emails, and closed-door discussions. Because once you accept that something is a process, the next question becomes unavoidable. What sustains it? The 27-minute interval is not arbitrary. It is too long for most natural oscillations, too regular for environmental noise, too stable for chaotic systems, and yet, critically, it is not perfectly fixed. Across decades of recordings, the interval drifts slightly, seconds over years, minutes over decades. Not random drift, adaptive drift, as if compensating. That detail is what finally broke the illusion that the signal could be safely ignored. Natural systems drift because they are influenced. Engineered systems drift because they adjust. Both imply feedback. This is where naming becomes dangerous, because to name something is to define its category, and no existing category fits. Calling it noise is inaccurate. Calling it signal implies intention. Calling it anomaly suggests eventual resolution. Each term carries assumptions that the data does not support. So, the safest choice remains silence. Not denial, not suppression, avoidance. At its core, this story is not about the ocean. It is about scientific confidence. Modern science operates on an implicit promise that unknowns are temporary, that given enough data, enough time, and enough funding, ambiguity collapses into explanation. The deep-sea signal challenges that promise, not because it is inexplicable, but because it is explainable only at the cost of admitting limits. Limits to classification. Limits to inference. Limits to what observation alone can resolve. Those limits are rarely stated explicitly. They are managed. Privately, many researchers have reached the same conclusion. Not about origin, not about intent, but about posture. The signal is real, it is persistent, it is not urgent, and it does not fit the question science is currently equipped or incentivized to ask, which means it will remain where it is, in the data, in the background, unresolved. So why does the signal remain unnamed? Not because naming it would reveal something terrifying, but because naming it would force science to say, we have detected a stable, repeating process in the deep ocean that we cannot currently explain and may not be ready to. That sentence is honest. It is also destabilizing, because it reminds us that observation does not guarantee understanding, and that some phenomena persist not because they are hidden, but because they sit just beyond the boundaries of what we are prepared to define. The deep-sea signal does not demand belief. It does not demand speculation. It demands patience, and perhaps, one day, a different kind of question.